Today we're going to be talking about kind of a different class of regressions known as classification. So, yeah, sorry, I also forgot my iPad today, so we're gonna have to work on the whiteboard today. So we've been starting with linear regression, and essentially we've been starting off with something like this. We have a continuous variable for y, and we have continuous variable for x, and then we started to get a little bit more complicated, right? And we have also looked at discrete variables for x as well. So does anyone remember what is it called when you have discrete variables for x? What do we call x? Yeah, so they're, okay, yes, factors, they're represented as factors in R, right? In the notes we've called them dummy variables or categorical variables, right? And so that is how we treat discrete variables for x. And so there's a question of, okay, what about if we want to do discrete variables for y? Okay, and there's immediately some kind of issue to think about here. So I have x and y. If I have discrete variables, that means I'm kind of running a regression, right? Let's start with an easy case, like a binary. I have a 0 and a 1. That would mean all of my values would be something like this, right? Okay, and so you maybe could run a regression, but that's, let's say that's kind of a departure from ordinarily what we're thinking. And does anyone see any problems here with doing something like this? No one sees any problems with this? This is great. We can all do this.
Really far from the observations.
Well, yeah, but like, okay, if you had something like this, you could legitimately actually say something about, like, right, the average value of x as it relates to when y is equal to 1, as well as the average value of x when y is equal to 0. It would give you some kind of information like that, right? But there's like something fundamentally wrong here, right? Which is, what values can y take? Yeah.
I guess if you have a linear model, you can get like negative values, which would be outside of the range.
Yes, in fact, you could get, right, if y's can only take, you're exactly right. If y's can only take values of 0 or 1, our prediction can take values of what? Anything, right? Literally negative infinity to positive infinity, right? Not only could I get all these values in between 0 and 1, I could get negative values, as you're pointing out. I could also get values above 1. So in fact, this idea of using a linear regression, it's not totally illegitimate if you're thinking about like this specific thing, right? But the line is not necessarily a good way to predict an outcome of 0 or 1, okay? So we need to come up with some kind of approach, some kind of model that is better suited to this, okay? So that is why we will be talking, or starting off with, logistic regression. So I'm sure some of you guys have heard of this, especially if you've taken some econometrics or regression class before, right? But fundamentally, the reason why we don't just do linear regression is this thing that I'm talking about here, right? It's because you're getting these values that don't correspond to your outcome. And we want to figure out some model that is better suited to doing that. Okay, so this is a regression model where the dependent variable is categorical. Which means discrete rather than continuous. Okay. So we're going to start off with a simple example for binary outcomes, right? In the same way that when we did this, discrete, we started with zeros and ones, and then we looked at more generalized categorical where you can have more than two. But we're going to start off easy. We're going to start off with just having two possible outcomes for a y. And I'll mention that this, so more generally, we figure it out when outcome is categorical. This class
Oh, okay.
of models is known as classification. We got it?
Yeah.
Sweet. Okay, thank you.
All right, thank you so much. Okay, thank you so much.
Okay. So we'll use the display for the code part, but we still use the chalkboard because I forgot my iPad. Okay, so classification. So logistic regression is a one type of classification model. There are many classification models, and we're actually going to cover some beyond logistic even today. But this is kind of the one that most people know about. In machine learning, they say you've got like regression and you've got classification, but that's kind of a stupid way of categorizing, because classification is still regression. Right? It's literally logistic regression is a type of classification. Yeah, so if you hear people talking about classification, it is just regression using regression where your response variable is discrete and not continuous. Okay? Questions? We're good so far. Okay. Erase. How much of a workout it is right on the board. Okay. So, we could have something like input going into some kind of model. And we might have some kind of binary outcome. Can anyone think of any examples of this? So we're used to, I think, at this point, models where we have continuous outputs, like what was the wages one, right? We predicted outcome of a continuous spectrum of wages as it relates to specific explanatory variables like your age and education and gender and race, right? So what might be an example of like a classification? Yeah.
I'm thinking input of changing to 0 a tariff for transit, and then the choice of the model is people using it or not. Just
Oh, okay.
yes,
So
no.
okay, so you have some set of inputs, right? And so this might be related to like demographics, location, etc. Going into some kind of model, and then uses public transit and doesn't use. Something like this, right? And so we can represent this as ones or zeros, and then you have a bunch of inputs. And the inputs are much in the same way that we've already discussed, just straight up inputs for continuous, and then dummies and categoricals as ones and zeros. But yeah, that's right. So again, this is a separate class of models that we're going to be using to help sort of evaluate these. Okay? Let me make just a little bit of room here. Okay, so I'm gonna do a little bit of kind of background here, just to kind of give a qualitative understanding of where the logistic function and regression kind of originates from. But this isn't necessarily too important to kind of memorize or anything. So in that earlier drawing that I had, where I had some points like this at 0 and 1, and then maybe I have some points like this, and then you draw a line like so. So I already discussed kind of reasons why this may not really be a great example of how to do this, but in fact some people still do this simplified approach for some classes of problems. And actually where I said, okay, your outcomes being just 0 and 1 makes it so that your predictions don't really make a lot of sense, right? Because you can get values that aren't just 0 or 1. But actually, the values that are in between 0 and 1 could represent something related to your outcome. Okay, does anyone have a guess of what that might be? Yeah.
If it's 0 and 1 and you get 0.2, 0.5, 0.7, you could understand as some, in this case, sometimes uses transit or has proclivity to use.
Yes.
Is around the area or some inference.
Exactly. So like, if I was at like 0.1 versus at 0.9, what might you say about your prediction relative to the outcome? Is it more, if I'm at 0.9, do you think that it's more or less likely to be at 1 or 0? What do you guys think?
More.
More likely, right? So in fact, Some people represent this as probability of x, right, is equal to beta 0 plus beta 1x. So in fact, that makes it so that the values between 0 and 1 mean something, essentially, and people actually still do this to some extent. And actually that would be a somewhat legitimate way of doing things, except for the fact, right, that your probabilities are unbounded. Unbounded probabilities. Okay? So, if you guys recall, if we want to stay in kind of the linear domain area, one of the things that we talked about before was actually doing some kind of transformations of your variables to keep it in the linear space, right? So the most obvious example that I talked about was when you do a natural log of a variable, right? So that you can transform something like this into something like this, right? So this is doing the natural log. Well, so it turns out you can kind of do a similar thing where we can try and do a transformation of the y. And so if the idea is that you want to bound things in certain ways, then I can do something like this. P of x over 1 minus P of x. So the probability of outcome divided by 1 minus the probability of the outcome is equal to beta 0 plus beta 1x. Does anyone know what this is called, by the way? P over 1 minus P? Does anyone gamble? What was that? The odds, yes. So this is known as odds. So if you are ever gambling or making a bet and someone's talking about odds, this is what odds refers to. It's the probability of outcome divided by the probability of the outcome not happening. Okay. So if I have an odds of like 3, right, that means the thing happening is 3 times more likely than the thing not happening. Okay. So, okay, why do we do this?
Bayesian?
Huh? Sorry?
Bayesian?
Bayesian? In reference to what?
Probability?
Yeah, so I'm not gonna get into that because we're gonna get a little too deep into the theoretical stuff, which is not the purpose of this class. But okay, let me just say, if I graph this, so this is my odds, something interesting happens, which is your graph now looks like this. So here, y, yeah, I'll just say y. Y can take on the outcome from negative infinity to infinity. What values can my odds take on?
0 to infinity.
Yes. So odds goes from 0 to infinity. Okay, so we're getting a little bit warmer here because now we're only unbounded in one direction. So unbounded in one direction. Okay. So we've done a little bit of magic here to go from this to this. Okay, that's all you need to kind of conceptualize here. We don't need to know how this is derived or anything. So it turns out, if I now take the log of my odds, P of x over 1 minus P of x is equal to beta 0 plus beta 1 x. This is known as the log odds. And you've now linearized this. But in terms of the y, the original y, it actually bounds you from, so this is log odds, but the y plot, y and x, ends up looking like this. So this one gets bounded from 0 to 1. Okay, and so essentially what's happening now is I can now do like a linear regression because you're on a straight line bounding between 0 and 1 in the original y. So, okay, you don't need to memorize this or know any of this. This is kind of just background for us to understand kind of essentially where the logistic originally kind of comes from. It's trying to deal with this problem that we've been talking about with this thing. Okay. All right. Let's take a look at an example of this in R. And we should be able to hopefully get a better understanding of all of this. All right. Actually, any questions before I move on to this? Studio, whatever opens up one day. Alright, let's try this again. I will note that in Canvas, I have loaded 2 data sets that we're going to be using for class today. So go ahead and go to Canvas and download those if you don't have them yet. Oh, we're having all sorts of technical difficulties today, huh? One second, I think there's something weird happening here. Oh yeah. Oh. There's like multiple things plugged in.
Oh yeah, this one is the one I'm using.
Okay, so I'll take this out, and that stuff was opening in the other display, and so I couldn't see it. Yeah, it's fine. I got
Because
it.
they're using this one, they're saying that there's a problem, so
Okay,
just some other source.
no problem. That also means that I have to keep doing this. Okay, that's fine. We can deal with it. Okay. This is gonna be tougher. Let's see. Okay. We are going to load in a data set from what I had under files in Canvas called election_parsed. We'll read that in, it's a CSV. Okay. And let's take a quick look at this data. Actually, I'll just open it up here so you can also see. So it's just two columns. We have a column Democrats won, and then this column here is the percentage of people in whatever area that's in that voted Democratic. Okay. Everyone following along, right? So technically you could win with under 50%, right? Because you could have like more than two parties running. But generally, right, we're gonna see hopefully a pretty good correlation between Democrats winning versus the percentage of people who vote for Democrats. Okay. Find the mouse here. Okay. So the way that we run a logistic model, I'm going to show kind of the simplest way, but we're going to actually use some packages later when we get a little bit more complicated. Okay, so what I've typed out, instead of LM, we're using GLM, which means a more generalized class of linear models. So that's what the G stands for. But the setup is pretty much the same. Dem.1 tilde %.dem. Then you specify the data. And then one new thing that I have here is family equals binomial. And so this is kind of describing the distribution of your response variable because it's got two outcomes. We are using this class where it's family equals binomial to describe that, so the function kind of knows how to treat this particular outcome variable and how to run the model properly. Okay? Okay, so I can run this, and I'll run this summary, and this is the outcomes. So we do have some residuals. The residuals are probably going to look a little bit different than what you're normally expecting, right? Because the explanatory variable is a little bit different. Okay, but we also have these guys here, we have an intercept, and then we have our coefficient values. Alright, so someone help me out here. Who can interpret this for me? If anyone remembers how to interpret for our linear regression, this is in some ways similar. Does anyone want to have a go at this? Okay. So as I increase the percentage of Democrats, or the percentage of people voting for Democrats, what changes by this much? Does anyone know? Yeah, okay, so let me make it a little bit simpler for now. As you increase the percentage of Democrats voting, do you get more Democrats winning or less Democrats winning? More. Okay, and how do we know that? What was that? It's positive, yes, thank you. So, because this is positive, we know that as this goes up, our outcome goes up. And yeah, like that's pretty much all I will conclude about this. You know, I can look at the significance and stuff and make some inferences from that. But, okay, the actual way that I would interpret this, right, is that as you increase the percentage of people voting for Democrats by like 0.01, or by 1, let's say, the log odds ratio increases by 48.29. Does anyone know what that means? Because I don't know what that means, right? So logistic regressions are typically a lot harder to kind of intuit the effect compared to a linear regression where we say, okay, you know, if this was a linear regression, I would say, okay, as you know, you increase by 1, this is the beta value, so your y will increase by 48.2. Okay, super easy to do that. But now it's not actually y that's changing, right? It's the log odds ratio. And then you have to like figure out as the log odds ratio changes, like how does y change? And it turns out that this number, the like marginal effect on y is not linear. It depends on like where you are, right? And so if you go from 10% voting Democrats to 11% voting to Democrats, the amount that affects y is different from if you went from 90% up to 91%. Okay, does that make sense to everyone? If you think about, right, the odds ratio, it's like a fraction, and so it's not like a linear way of changing, of like understanding what the marginal change is. Whereas in a linear one, that wouldn't matter. Okay. Yes?
So to what extent would we use this?
Yeah, so great question. You still kind of, if you want to run a logistic model, you still do this. And you would end up with this table. But actually a lot of people, they, if you look at people who use logistic regressions in their study, in research, a lot of times they'll run this and they'll say like, okay, these things are significant, and so this is an important thing, and it has a positive effect, and then that's it, right? A lot of people do that. Okay, we want to do a little bit more. We want to be able to say a little bit more about this. And so I would encourage you guys, when you're doing these types of models, actually, you can still get good intuition on what's happening here, but you have to do a little bit more work. There's a little bit more stuff that we can do here. And let's talk about what that is. to create a new data frame to predict on. Because what, kind of as I was mentioning here, the thing that's actually getting predicted by these outcomes is actually probabilities, probabilities that effects are happening. And so I can actually draw out the probability curve that is generated by this model, and that's going to give me a better intuition about what the outcome prediction should be, rather than these like coefficients, which like don't really mean that much to me. Okay, so what I've done here is I've created the data frame in which I'm predicting over, and I'm just going from 0 all the way up to 1 in increments of 0.01. I'm going to do that prediction, and then I'm going to plot it. I'm going to use ggplot. Okay, so I'm putting in the new prediction data for X and for Y. I'm going to have a line plot, and I'm just going to label these proportion. Oh, sorry, it's not the number of people who vote for Democrats. It's the proportion of registered Democrats in that area, which is, I guess, going to be close to probably the same thing. Okay, so what does this look like? So like I said on the blackboard, right, your y ends up getting bounded from 0 to 1 based off of the linear line of the log odds plot. And now I have this plot. Okay. So if I want to say something about your outcome, the probability that a Democratic candidate wins, what do you guys think? In order to tell me about that outcome, is this more useful, or is the probability plot more useful? Or neither?
The plot.
The plot, yes, great. And so this is what I was meaning by the change is not linear, right? So if I go from 25% registered Democrats to 30% Democrats, right? That's a 5% increase, but it doesn't really do anything. But if I go here to here 5%, that could be like all the difference, right? That could change the probability quite a lot. And so that's what makes this part a little bit less intuitive, because you have to calculate to a specific point to understand the marginal change. But yeah, so your proportion, or your probability of an outcome happening depends on how your x changes, and it's always described in this shape in the logistic regression. Okay, the like rate at which this goes up might be really different depending on the context of the problem and the data, but generally it will always be this sigmoidal shape. Questions? Okay. Let's go back to the board. So a little bit more background. So unlike an OLS, logistic regressions are solved via maximizing log likelihood function. Rather than minimizing the sum of squares. Okay. So remember in OLS we kind of have these like distances from your prediction line. That is not how logistic regressions are calculated behind the scenes. They use something called the log likelihood function. And this is not something that you have to memorize. This is essentially what the computer is doing behind the scenes. So this is a function describing the plausibility of a model parameter value given specific observed data. So I'll write the equation. It'll look something like this. This is, again, just kind of for your reference. This will be in the notes as well. Okay, I'm not even gonna write the simplified form. So different, it's calculated, the parameters, beta, are calculated differently from the way we calculate betas in the OLS. And one of the features to kind of remember is that in OLS, our betas in smaller size problems, right? We talked about how there's actually an analytical solution, right? So you have, remember this thing, beta is equal to x inverse xty, right? So this is something that I can like straight up just solve. Turns out for a log likelihood function, we don't have that. So this is actually an optimization problem, and it kind of iterates to solve this. And so You will oftentimes see this, like when you solve a logistic regression, it'll tell you like, oh, this is how many times it like iterated to arrive at that value. It's going to be an imperfect value, right? It stops at some like threshold, but fundamentally, our betas are now being calculated in a different way than with the OLS. Yeah, the way this is done, if you're interested, set partial derivative dl d beta j equals to 0 and approximate numerically. Okay, and that's how you calculate betas. This is like the behind the scenes stuff of what your computer is actually doing. Okay, one last thing before I move on to a more generalized class of the logistic known as multinomial logistic. This is an important concept to remember. So this is probability of an outcome, and this is my explanatory variable, right? And we have this logistic function. So, okay, what was in the example I just gave, what was the outcome variable? It was just there, you guys.
The Democrat winning.
Yes. And okay, and a little bit more specifically, the Democrat wins when you have y equals 1, right?
Sure, yeah.
Yes. So this curve actually gives a little bit more hidden information. Okay, and that information would be what? There's another curve, right? This is the curve that describes the probability of your outcome for y equals 1. What is the curve that describes the outcome for y equals 0? What do you guys think? What is the total probability of all outcomes? Yes, I saw it. 1, right? You can never have higher than 1. Well, the probability of all things happening is 1. Okay. So if this curve describes y equals 1, what do you guys think the curve looks like for y equals 0?
Flat.
It would be the opposite, right? It would look, okay, that's really bad drawing. It would look like this. Y equals 0. Okay, so if I stick my hand here at any point in x and I add up the dotted line plus the solid line, it should always equal 1. So in your logistic regression, this is very much in the same way, right? When we do dummy variables or categorical variables in our linear regression, remember we would leave one out, and that would be getting described by the default by like the intercept, right? Here, you're kind of doing the same thing. You're always leaving one of your outcomes out, and you can figure that out based off of everything sort of adding up to 1. In this case, there's one thing getting left out, but when we go on to multinomial logistic, right, we have more than 2 outcomes for y, you'll end up getting many probability curves leaving one out, and the last one can always be derived by doing 1 minus the sum of all the other ones, okay? This is an important concept, so anyone have any questions about this? Okay. Print. Okay. Next up. Multinomial logistic. So this is a generalization of logistic to multi-class problems. So for a binary outcome, which is what we just talked about, this might look something like this. F of k comma I is equal to beta 0 k plus beta 1 k times x 1 I. So this is an index for our outcome index, and this is our observation index. Okay, so we got some data here, and then these are like ones and zeros, right? Okay, so for this data set, how many k's are there? Yes, k equals 2, right? There's only 2 possible outcomes, 1 and 0. And then our I is equal to the number of rows. We could have multiple outcomes. And in this case, we would have something like k comma I is equal to like a vector like this. And so now k can be greater than 2. This actually means that for any single outcome, you're gonna have multiple, or for each outcome, you're gonna have multiple betas associated with it. Right, so this is gonna look a little different from our linear regression. Okay, I think the easiest way to visualize this is through an example. So we will jump over to R. gonna use a data set, the other data set that's in Canvas called Disney. Okay, and what is in here? Let's take a look. So these are movies and TV shows. It tells you the year, a certificate, which is like the movie rating, how long the runtime is, the genre. So the reason why I don't say where it's called certificate instead of movie rating or TV rating is because there's actually another column called rating, which is like the rating, right? The rating that people rate the movie at out of 10, and then the number of people who voted to give that average rating, and then it gives information about the it's like this, the highest profile person from that TV show or movie, and that's usually in reference to an actor, actress, or director. Okay. We're not going to use a lot of this data. In fact, this is like not the best data set to do this, but it works for the example, so someone has a better data set to do this in the future. I'm all ears. So essentially, I am going to be trying to run a classification model where we want to understand the relationship between the movie certificate, right? Whether the movie is, so we're actually only going to be looking at movies, and we're going to look at how a movie certificate, if it's like R or PG-13 or PG or G, can we get some understanding of those certificate ratings as they relate to the length of the movie and the rating score of the movie. Okay. So I am going to filter out some information. Disney.filtered. And I'm just gonna grab the information that I was referring to. So I want to, from the original data set, only select rows where the certificate is R, PG-13, PG or G, which will exclude all of the TV shows because the TV shows don't fall into these certificate ratings. And I want to include a little bit of filtering here. I'm going to get rid of, this just makes it a little bit nicer. I'm going to get rid of movies that are less than 200 minutes, or no, sorry. I'm going to get rid of movies that are greater than 200 minutes, and I'm going to get rid of movies that are popular rated less than 3. So including things less than 200 and including things greater than 3. Okay. So create that data set. Okay. And then you will need to load in a couple more libraries here. So you can do this in GLM, but there's a couple of packages that kind of make your life just a little bit easier that I will use. So NNet is a package that is specially designed to deal with multinomial logistic regressions. And then effects is a way that we can more easily generate predictions.
Sorry, library effects does what? You more easily,
I'll show you in a second, but essentially what it's gonna let us do is generate predictions a little bit more easily. Okay. Okay, so instead of GLM, I'm going to use a function called multinom. This is the thing that's coming from MNet. Oh, and I should load these libraries myself. Okay, so I'm going to run certificate on runtime and rating, as I had mentioned before. And then we are going to get a look at the model results. Oh no. Oh, that's because it's certificate and not certificate. Certificate. Okay, great. And actually as it runs, you're gonna see this thing happening. This is that iteration thing for solving for the log likelihood. Just some kind of extra information for the iteration. And this value that it's talking about here, I believe is the log likelihood value. And once it converges to a number, right? So what's happening is, or no, this can't be the log likelihood, it should be going up. Yeah, but it's associated with the log likelihood in some way. And it converges to the value, and we should see results that look something like this. Okay, so okay, what are we looking at here? So if you recall, I mentioned over here that for every outcome, you're actually going to have your own set of coefficients, right? And so that's actually what's being displayed over here. So the outcome PG has a beta 0 of negative 0.145. It has a beta of 0.0119 for the runtime, and it has a beta of negative 0.079 for rating. And likewise, you know, your other outcomes will have their own beta coefficient values. And we can use these coefficient values to essentially describe the individual probability curves related to each outcome, right? What's missing here? What are the possible outcomes? G. Okay, you were answering my previous question. Yes, the possible outcomes are G, PG, PG13, and R. We are missing G. And so how do we derive G? The
1 minus.
Yeah, that's right. And so that when I build out the probability curves for each of these things, you can calculate the probability associated with G by subtracting 1 minus, you know, whatever point that you're at along the curve. And the standard errors associated with each of the coefficients are here. Okay? Questions about this?
I'm sorry, it's the rating which will equal 1, yes? The sum of the rating?
No. Wait. to which rating are you referring to? So the certificate rating, these things. So there's some probability that the movie is rated R. There's some probability that the movie is rated PG-13. There's some probability that the movie is rated PG. And there's some probability that the movie is rated G. And it has to be one of those four things, right? Those are our only four outcomes. So if I add up those probabilities, it'll equal to 1. Okay.
So
Yes.
would you get the same result if you turn them all into dummy variables and run 4 different models?
So if I'm following what you're asking, yes. But like, I think what you're saying is, if I did something like this. Actually, let me do this. Okay. So x1, x2, x3, and y. And so like R, G, R, PG 13, PG, R. Okay. So maybe I'll do something like, no, we'll just do it like this. And then you have values here. Okay. And you put this into an MNL regression, and then for R, you get let's call it beta 1 R, x1 plus beta 2 R, x2 beta 3 R, x3, something like this. And then for G, you get something similar, right? Would be beta 1 G, and so on. So when you say run it separately, I think I'm visualizing something like this.
What I mean is like you make a new Y that's either 1s or 0s, it's rated R, it's not rated
Yeah,
R.
yeah, exactly. That's what, so it would be, I'm just gonna say R, and then I'm gonna put 0 if it's not R. So 0, R, 0, 0, R. And you have the same stuff here. This will be the same.
Right.
Yes. But like, this stuff won't.
Well, it wouldn't be, you wouldn't even get those results.
You wouldn't. You would get, yeah.
Yeah.
So like, this, you would get, we tried different colors, but okay. This, let's say, this is your R curve. You would get, you know, some other curves here. This might be your G curve, this might be your PG curve, and then this might be your PG-13 curve. I don't know. So if you ran this, you would get this, and if you ran this, you would get your same R curve, but you wouldn't have information about the other three. You would have a generic, like, not R.
Right.
Yeah? Okay, yes. Yeah, I'm like 99% sure that this is what would happen. Yeah. Okay. so, right, if you wanted to run this, or if you run an MNL, you could do the nnet package, use the multinom, and it would quickly be able to generate you all of these coefficients. It is a little bit harder to generate those probability plots, but let me, so okay. You don't have to follow along for this part, so I'm just gonna copy and paste the big chunk of code that I made to kind of help facilitate this. But I can kind of walk through this. Let me get rid of.
Can I ask another question?
Yes.
Before we move on. So how would you put the interpretation into words for that first model with multiple?
Yep, sure. Let's take a look at that. So this is kind of analogous to how would I do the interpretation of this stuff. In our first model, we had this stuff, which I said, okay, I can like interpret by having an understanding. Okay, so people often don't try and like interpret the log odds ratio. They say positive and significant. Okay, and that does give some basic information, right? And so here I can say something like, I can't really eyeball and say the significance thing, but let's just suppose that these are significant. Well, one, you could say, oh, which things are significant, right? As in, what things do we actually think have an effect on outcome? And then two, you can look at positive or negative to say if the longer the runtime is, right, the more likely that that it's, you know, PG-13 relative to the other two, right? And then same with the rating, what's more or less likely just based off positive or negative. I wouldn't really go beyond that just because, yeah, log odds ratio interpretation is weird. Okay, but the thing that I would do is this. I would generate these plots, and so you guys can take a look at these to kind of get a sense of how this is done. But let me show the curves first, and then we can talk about interpretation and possible issues. Oh no, what is happening? I see all sorts of, okay. So back up for a second. What are our two explanatory variables in this model?
Runtime and rating. Runtime and rating?
Yes, runtime and rating. Okay. So if I just look at the rating, popular rating, right, not the certificate rating, then we can see something like over the range of ratings, right? If the ratings are really low, there's a much higher probability that the movie is rated PG. Okay. As the ratings go from low to high, it doesn't really change the probability that the movie is rated G very much. Okay. And as the ratings go from low to high, it tends to increase the probability that the movie is rated PG-13 or that it's rated R. Okay? And I can actually see kind of exactly how those probabilities are changing, right? It's going from like 50% down to like 30% for PG movies. Okay? So I think that this oftentimes is like a better visualization or gives a better understanding of the effects of your explanatory variable on your outcome compared to compared to all of these errors, compared to this. Okay. I can, yeah, from here, like I might be able to say something about like PG is negative, right? As it relates to rating, so as rating goes down, it's less likely to be PG, and we see that here, right? But I think I have like a better sense of what's actually happening here compared to here.
Yeah, basically, if people like it, it's probably PG-13.
Yeah,
Or maybe.
maybe. Okay, importantly though, and the reason why, actually, so this is gonna go back to why I'm using this package and what makes it slightly easier. Remember that I said that the marginal effect, right, it's nonlinear and it depends on where you are in this range. But what's missing? Think about that. Runtime, yes. So these set of curves are in reference to a fixed runtime. So if the runtime is different, these curves may look different. Now the trends are actually going to be the same, but like the magnitude to which these things change might be different. Okay? So you can almost imagine this as a 3D plot. If ratings goes this way and our outcomes, the probability of the outcome is this way, imagine that runtime goes out this way, then these curves may kind of look different in 3D. Like the slopes are not just gonna be like straight out like this, right? They may actually change at different runtimes. So the effects package makes the generation of these plots a little bit easier because you don't have to come up with a whole vector of different things. So in this case, it wouldn't be that hard to do, where I look at all combinations of ratings and runtimes. I could do that, plug it into the prediction, generate these plots. Okay. So suppose that there were 10 possible ratings and 10 possible runtimes, then I could generate a bunch of probability plots. There'd be 100 combinations, right? But suppose you added one more variable, and that had like 10 possibilities, then you're up to 1,000 and so on. And so to generate all of those possibilities, to do a prediction plot gets harder and harder. With the effects package, what it does is, okay, it says, okay, if you want to look at the range of ratings, let's fix the runtime at the average. So these ratings are what the probability plot looks like for the average runtime. And I can do the same thing for runtime fixed at the average rating. So that looks like this. Okay? So if our movie is at an average rating, then the longer the movie it is, the more likely it's PG-13. And the longer the movie is, the less likely that it's rated G. Okay? Yes?
I have a question. This is 4 categories and 2 parameters. Ratings and runtime.
Yes.
It could be 10 parameters, 10 variables. Is there
Yeah.
a common sense to not to do too much, or do significance first and take out correlation, or just do it?
Yeah. So model selection, right, which is what you guys talked about last week, a lot of the same principles apply for this. You know, the number of outcomes, that's just whatever your explanatory variable is, and so, you know, that's dependent on kind of your research question. The number of parameters to include is gonna have to do with a lot of those model selection criteria that you guys went over last week. Those still apply in the logistic regression. Okay. let's say I am at the largest, sorry, I'm at the average rating, and I want to do a prediction now. Okay, so predictions are a little bit different, right? Because we're now talking about probabilities. Let's say we're at this runtime right here. If you had to put money on it, what would you guys predict would be the certificate rating of a movie with a runtime at this 1.5 index? G, this red one. And why do you choose that?
I feel like I spoke too soon, but just because it's like has the highest probability.
Yes, you didn't speak too soon, that's right. So, when it comes to prediction, oftentimes the way that these regressions are done is it simply takes at any combination of runtime rating value, it just takes the one with the highest probability. Okay, so here I would predict G. If I'm here, I would predict, oh sorry, no wait, PG, yes, PG. And if I'm over here, I would predict PG15. Okay? And actually in this case, I would never predict R, but you know, as I said, it could be different at different runtimes. Maybe this kind of goes up when you have like a higher rating or something.
So in both instances, you just set kind of the frame that we're looking at to the average runtime or the average rating, but you could set it to any
Yes.
one more. Okay.
Yeah, and in fact, I can, let's actually look at that. So I'm gonna do a prediction, but this time, okay, again, you don't have to follow along. I know I'm kind of like copy and pasting here. We can look at this. You can look at this in the notes, but let me explain what's happening here. I'm going to create a new data set using this expand grid thing. And you can see it's sequencing across all possible runtimes and across all possible ratings. So I'm looking at all combinations of my inputs, and I'm going to predict over these. And I'm going to use the original prediction, and this prediction is actually going to return outcomes based off of the most likely thing that happens. Okay. Is everyone following along? Right, so I have the shortest possible runtime, the lowest possible rating, shortest, middle, and so on and so forth. All combinations of ratings and runtimes, plug it into the model, and I want it to spit out back to me what the certificate is, which would be the highest probability prediction for that combination of rating and runtime. So, let me just run this. And, okay. So the expand grid part gave me all of these, runtime and ratings, and then when I predicted, I added this as a column, which is gonna give the prediction. Okay? And just to show you what that looks like. Let me first do this. So this is the original data. Looks something like this. So we're kind of working in 3 dimensions here. So runtime, ratings, and then certificate values. And the color refers to the certificates. Red for G, blue for PG, green for PG-13, and purple for R. Okay? So I can predict across the full range. That was the thing that I just showed you with the table, and I'm going to show you what the predictions would be over the original data. Okay. So the circles with black outlines, these are the original data. Actually, let me zoom on this one too. Okay, so it looks kind of like this. And actually these, like linear boundaries is like actually an artifact of the fact that we're kind of still in a form of some kind of like linear regression. You create these linear boundaries. And so this, if we assume that the boundaries are linear, this is the model produced through our MNL that will give like the highest overall probability of like successful answers, right? MNL is constrained to make boundaries linear, but this is like essentially the best that it's gonna do to give us the most like positive results, right? And so if you have a red dot here, right, you will have successfully predicted it, but it will incorrectly predict anything that's not red here. It will incorrectly predict anything that's not blue here, and so on with the green. So this is kind of your result for multinomial logistic. Okay. Yes.
So is there a model that whose boundaries are not linear, and is there
Yes. Yeah. Well, we'll look at them, and we're going to look at it right now, actually. But before I get to that, I will note that this model predicting in this way is purely an artifact of our decision to calibrate the model via this log likelihood function. And what that is doing is it's trying to maximize the number of times I get something right in the prediction, right? Under the constraints that I have to do these like linear borders. That may not always be what you want to do. And there are a whole class of other outcomes that you might want to care about. And And so this is something important to consider anytime you are doing classification work. Correct. So let's say. So true values and predicted values. Okay. So here, you guessed correct. And you guessed correct. Here, you guess, let's say you guess correct, but answer is wrong. And here is you guess answer is wrong, but actually correct. Okay. So let's say you have something like this. G, R, G, R. Let's say you don't know the certificate rating of the movie. All you know is the overall rating and the overall runtime of the movie. I can go into my model, and sometimes I'm gonna get it right. So this is actual, and this is model prediction. So you're with your kid and you're trying to figure out if you should watch this movie or not, and all you know is the runtime and the rating, you don't know the certificate. And you're like, okay, I'm gonna rely on my model to tell me if the movie is rated G or R. And sometimes you'll get it right and you're like, okay, I'm gonna watch this movie with my kid. Sometimes you'll get it right on rated R and you'll be like, I'm not gonna watch this movie with my kid because it's rated R and they're too young. Okay, great. So this is great when this happens. What if the movie, what if you predict that it's R but it's actually G? So you say, well, the model says it's R, I'm not gonna watch this movie. So you like miss out on watching a movie. And so you, your model did poorly and you miss out on an opportunity to watch a potential G movie. Okay, now what if your model predicts that a movie's rated G, but it's actually rated R, and then you start watching it with your kid? That's like extra bad, right? So super, super bad. Does anyone know what this is called? Anyone heard of type 1 error, type 2 error? Yeah, so that is this concept, right? So the like famous example is like for medicine, if you like predict whether someone or not has cancer, yes or no, and whether or not you predict they have cancer, yes or no, right? So a lot of times, one of these outcomes is a lot worse than the other outcome. So in the default multinomial logistic, we may, you are trying to get as many right guesses as possible. But it turns out that sometimes you may want to avoid getting certain outcomes more, or you may, prefer to actually overestimate this and get this a little bit better, or underestimate these things and get one of these things better. And so you can actually do that, right? And so one thing that I just want to kind of turn your attention to is in classification problems, think very carefully about your type 1 and type 2 errors, and that you may actually want to recalibrate your model to care more about avoiding some of these outcomes as opposed to getting as many things correctly as possible, right? Does that make sense to everyone? Okay. So, anytime you choose to weight one of these things, your overall prediction success will go down. But you may be willing to do that to avoid this situation from happening and getting more errors in other places and lowering the success rate of these guys to avoid this. And that is an important thing to consider when doing classification. Okay. Any questions? Okay. Don't have a great deal of time. All right, let's get started on one more thing. I probably won't have time to do the example in R today, but we'll start off with that on Wednesday. So, you were asking about other classification methods besides logistic. And so, let's talk about one of those. Okay. Another classification. This one is highly non-parametric, which we actually haven't really gotten to yet. But this is a useful one to talk about. So I'm going to write the math, which is just for reference. I think actually the mathematical formulation is highly unintuitive, but this concept itself is actually very intuitive. Okay. So what is this describing? Given a positive integer k and test observation x0, identify the k points closest to x0 represented by n o. So it estimates the probability for class J as the fraction of points in n0 whose response equals J, and it classifies x0 to the class with the largest probability. Okay, what the heck does that mean? It's actually really simple. Okay, let's do this. Okay. Let's do, let's say, right there. Okay. Is question mark in X or O? So, at k equals 1, k equals 1 means I look at the first nearest neighbor. So who's the closest point to the question mark? It's this circle. Okay? So a question mark would be a circle. K equals 2. What would be my next closest point? Over here. So it's tied, and so actually it's going to go to, I believe the previous one, if it's tied. K equals 3. I'm going to look at the 3 closest points. So that's going to be this circle, this x, and this x. So question mark would now be an x because there's more x's than circles. Everyone following along? Alright, what about k equals 4? So the next closest point is over here. Question mark is a x. Yes. Okay. K equals 5. What do you guys think? Probably this one. How many circles? How many x's?
2 circles.
2 circles, 3 x's. Question mark is therefore
X.
still an x. That's k nearest neighbors. Everyone understand? Okay, a couple things. 22, 23, 24, 25. Okay. K equals 25. What would my question mark be?
Thanks.
X, Y, X.
Just because of the trend, there are more X's.
Yeah, there's more X's than circles. Right? So there's, I'm pretty sure there are 5, 6, 11, 14, yeah. 14 out of 25. Yeah, and so when your K is really, really big, the prediction will always just be the thing that has the most points. Okay?
I just want to ask for number 2 for K2. It is O because of the precedent set?
Yes.
Okay, thank you.
Yeah. Okay. What's the correct number of Ks to use? What do you guys think?
An even number?
No, not necessarily.
Largest possible?
Would that, okay, so, let me see. If I did the largest possible, if I did K equals 25, and I put a question mark here, that question mark would be what?
0.
No, it would be an X, right? Because you're looking at all 25 neighbors. So your question mark will always be an X because there's more X's than circles, and I'm gonna look at every possible neighbor. So maybe I'm looking too far, right? Because doesn't this seem like it should be a circle,
Yeah.
right? So if this is kind of like underfitting, and maybe this is like overfitting, then the sweet spot might be somewhere in between. So how do we determine the sweet spot? I'll probably ask this question many times for many different models, and whenever I ask a question like this, the answer is going to be cross-validation.
I was gonna say that.
Yeah. Okay, so it was on the tip of your tongue, but, right, if I left out some of these circles or I left out some of these X's, like I can do a test set and compare across different Ks, right, and be able to say, okay, at which K choice will my out-of-sample validation give me the best predictions, and that's probably going to be your best K, right? So, cross-validation still coming up here. It's going to be coming up for lots of different models, that kind of principle. But this is, right, finding the sweet spot between underfitting and overfitting is, we're fundamentally always going to use some form of cross-validation. Okay, so that's it for today. Next class, I'm going to start off with this example in R. We're going to repeat the Disney example, looking at this method instead of logistics.